Bem-vindo à sessão de modelagem geométrica e geometria computacional do Sibgrapi 2012. Welcome to the Geometry Modeling and Computational Geometry session of Sibgrapi 2012. We have four papers today. The first one is approximating implicit curves on triangulation using affine arithmetic by Paiva, Nascimento, Figueiredo, and Stolfi. And Afonso Paiva will give the talk.
Thanks, Luiz Henrique, for the introduction. And this work, the problem is, given planar triangulation, we want to approximate an implicit curve on this mesh. Okay? But the possible solution is the curve location. It means we need to compute the intersection between the curve and the triangles of the mesh. But the question is, what criteria do we use to do that? Our first choice could be a Martian triangles algorithm. And if we perform the Martian triangles algorithm, you have this result. But this result is not very good because we lost the topological information of the curve. Okay, so we can improve this result combined with mesh refinement because small triangles imply in more details. Okay, so if combine this, but more questions arise: how small are the triangles and how efficient is it? Okay, if we combine this, with March triangles with the mesh refinement, we can have this an acceptable result like this, but it's not efficient because we need to evaluate it. We need to test if the sign of the function on each vertex of the triangles changes in triangles far away from the curve. Okay? So for this reason, our main goal are to provide an algorithm with spatial and geometric adaptation. And one preview of our method is showing the right side. Okay? We can compute the implicit curve with few tests of the mesh. Okay, and we need some numerical tools to provide to build numerical oracles, and these numerical oracles must be answered the following questions. The first one is this triangle away from the curve? The first one. The second one is the curve is approximately flat inside the triangle. And for build this numerical oracles, we use the self-validated arithmetics. Self-validated arithmetics provides interval extension, an interval estimative for a real function. Okay, if we have with theoretical guarantees, it's very important. If you take the interval extension of the function, we have this relation. The interval extension contains the image of the function, okay? And this relation provides to us a robust test. This test, a robust rejection test. If 0 is not inside the interval extension, then the cell X is away from the curve, okay? And two examples of self-validated arithmetic methods are the interval arithmetics and affine arithmetics. Affine arithmetics is a remarkable numerical method introduced by João Combe and Jorge Stoff in Sibgrapi 93. And affine arithmetics represents a real quantity z by this expression where each value z1 is a real number and the values epsilon1 until epsilon n are the noise symbols, and these values is in the belongs to the interval -1 and 1, okay? We can compute arbitrary formulas on affine forms. It's very important. And it's a good alternative to replace interval arithmetics in computer graphics applications due to these properties. I will not emphasize these properties, but another important feature of affine arithmetics is affine arithmetic algorithms can be input and output intervals. We have a conversion between interval and affine forms. Okay? We can, given an affine form, given by this expression, you can't take the range of this form by this another expression, or this delta is the sum of the absolute values from z1 to zn, okay? And we can convert interval form to affine arithmetic. Given an interval AB, you can write the affine form of this interval, take z0 as the midpoint of the interval, and the z1 as the half of the length of the interval, okay? And now, the first we compute bounds for the implicit curves with strips on rectangles, okay? So given, in other words, we need to evaluate the function, the real function f with affine arithmetics. Given a rectangle, we can write this rectangle as the Cartesian product of the interval AB and CD, okay? Now we take the center point, the centroid of the rectangle, and the value x1, it's the half of the interval AB, and y2, it's the half of the interval, half of the length of the interval CD. We can represent any point inside this rectangle by these two affine forms, okay? We have an affine form to approximate the x coordinate and another affine form to represent the y coordinates, okay? So we have the affine extension of the function f given by this expression, and these terms from epsilon 3 until epsilon n represent the terms related to non-affine operations. For example, multiplication, exponential, sine, cosine, etc. Okay? Now we can condense the second order terms in a single term. Taking the sum of the absolute values from f3 until fn, and replace this expression by one single term, okay? Now we can build our first numeric oracle. We take 0. If 0 is not inside the range of the affine form, then we discard the rectangle, okay? And we can construct geometric bounds using affine arithmetic form of the function f. Note that we can replace epsilon 3 by -1 and 1. In this expression, you have two parallel planes that surround the graph of the function f, over the rectangle, okay? But there's a problem here, because z is written in terms of epsilon 1 and epsilon 2, and our implicit curves lives on the Cartesian plane. So we want to convert we need to change the coordinate system. We can't replace the variables epsilon 1, epsilon 2, and rewrite this in terms of x and y. And we can do this just isolating epsilon 1 and epsilon 2 in these equations, okay? And replace in this last equation. So isolating epsilon 1 and epsilon 2 from the affine forms of x and y, and replace here. Now you can the two parallel planes in Cartesian coordinates, okay? Now you take the intersection of these two parallel planes with the Cartesian plane, just replace the value z by 0, okay? Now you have two parallel lines which contains the zero set of the function, okay, in red. Now we can compute, also we can compute the width of this strip, okay? We compute the width of this strip using the distance between two parallel lines, okay? It's very important because it's provided to us a good estimative for the curvature without use the derivatives of the function, okay? This example, we take an ellipse, okay? Note that in regions of high curvature, you have wide strips, okay? So now we can build our second oracle. It's if the wide is more than a user threshold, then you subdivide the cell, okay? Now we compare our approach with the interval arithmetics-based method proposed by Hélio Lopes et al. In Sibgrapi 2001, okay? The Lopes approach uses adaptive quantity to subdivide the space. You can see in this image, now the right side is ours and left side is the Lopes approach. You have much more cells to explore using interval arithmetics than affine arithmetics. Some statistics you can show here. You have almost 7,000 cells to visit, and in our case, we have a little bit more than 1,600 cells, okay? The number of the leaves of on the quad tree here, computational time here. It's more important, it's the affine arithmetic provides a quadratic convergence for the curve, okay? Now we will extend this concept to compute bounds to implicit curves with strips on parallelograms, okay? We need to evaluate f, the function f, on a parallelogram with affine arithmetics. To reuse the previous framework, we just need to write epsilon 1 and epsilon 2 in terms of x and y, okay? Now, given a parallelogram, we have the centroid of the parallelogram, the point x0 and y0, and have two parallel vectors, v1 parallel to this side, v2 parallel to another side, and the length of the v1 is the half of this edge, and v2 is the half of the another edge, okay? So v1, the coordinates of the v1 and v2, and we can write these quantities in these affine forms, okay? Now we can note that these quantities are dependent because they share the same symbols here, okay? Moreover, you can write these equations in a matrix form. So to write epsilon 1 and epsilon 2 in terms of x and y, you need to compute the inverse of this matrix, okay? But the question is, this inverse, the matrix is invertible only if the parallelogram is not degenerated, because when this occurs, the vector v1 and v2 are linear independent, okay? Now finally, bound implicit curves with stripes on triangles, okay? The idea is replace the evaluation of f on triangle by evaluation of f inside a parallelogram, okay? The first choice is include a triangle into a parallelogram. You can use we can choose one of these three strategies, but it's conceptual. This one of them is conceptually wrong because we will evaluate f outside of its domain. Okay. Moreover, it doesn't not work for surface. Another possible solution is to split a triangle in three parallelograms using the midpoints of each edge of the triangle. Okay. And we adopt this one to avoid to evaluate f outside of its domain. Okay. Now let me show you the step-by-step of our algorithm. Then, given a triangle, we want to approximate this parabola. Okay. The first step, we split the triangles in these three parallelograms. Then we compute the affine extension of f evaluated on each of these parallelograms and have these stripes, these gray strips. Okay. If the test passed by our two oracles, then we approximated the curve by splitting the triangle in 4 subtriangles and compute the intersection of these subtriangles using bisection method, because if you use linear interpolation, we have some cracks can appear in this reconstruction. If the test pass, we need to subdivide the mesh. Okay, it's very important because our method does not distinguish if the input mesh has or not a topological data structure. Okay, you can use our method with triangle sup, in other words, a mesh without connectivity, or mesh with connectivity. In this case, we choose as subdivision rule, the midpoint splitting. We're splitting the triangle in 4 subtriangles. In this case, you use for 8 meshes, okay? Now the results, we have much more triangles in that case, and we will zoom this image. You can see you have, in that case, you have T nodes on the vertex. In this case, we have a conformal mesh. Okay. The effect of the geometric criteria in our method, you can see regions of high curvature, you have small triangles. In regions of flat, in regions where the curve is flat, you have big triangles. And now some results. Our method we can do with mesh with complex topology. Work in progress, with a little bit more computational effort, we can extend our method to compute approximation of implicit curves on surface, okay? Now, in this example, we have a bit-torus mesh and one function given implicitly by this equation, the unit sphere. You want to compute this curve restrict on the mesh. Okay, now you have the curve on the mesh with 4 connected components. Okay. Questions?
We have time for questions, please.
Hi, Afonso. Very
Hi,
nice
Doug.
work.
Thank you.
You have an epsilon there that controls the subdivision process. is there a chance that you're missing some component or you're altering the topology if the epsilon is not properly chosen?
Good question. In our case, it's not happen. If only you choose a big epsilon, but it's controlled by the user. You can choose a very small epsilon. You can stress this value.
I see. And can I have another question? Okay. I saw you showed one image with self-intersection.
Okay.
If you go back a few slides, yeah, there. I'm impressed. How can you handle self-intersections with this? I mean, is this a coincidence, or can you have an arbitrary number of self-intersections, and you can, solve the correct topology?
This is a coincidence because you can take a large mesh, you can find another component.
Okay. Nice.
Okay, thanks. Have you thought of extending your method for handling convex cells? Let's say like your grid is now a Voronoi diagram and you're thinking about Voronoi cells. It's convex cells, right? So maybe.
No, because I don't know, because you have some symmetry. Our method is based in parallelograms. If you can split a Voronoi cell
In
into
triangles, right? Maybe I don't know.
parallelograms.
It's on the top. It's true. Yeah. Okay.
Any further questions? Anyone? If not, let's thank the speaker.